Hello, this is Dr. Grande. Welcome to my video on an introduction to the chi-square test. As always, if you find this video useful, please like it and subscribe to my channel. I certainly appreciate it. The chi-square test is a non-parametric statistic, also known as a distribution-free statistic. And we often use chi-square when we have a research design that produces data that violate the assumption of parametric statistics. For example, the homogeneity of variances assumption is violated, or the normality assumption is violated. The chi-square is used to examine differences in categorical variables, and it comes in two types. There's two types of chi-square: test of independence and goodness of fit. We use the test of independence when we have two variables and we want to see if there's a relationship between those variables, and we use the goodness of fit when we have one variable, one set of observations, and we want to compare that to the expected observation. And I'll give examples for those two types in a moment. The null hypothesis for the chi-square test is that there is no relationship between the variables. So the variables are in fact independent. The alternative hypothesis would be that the variables are dependent. So let's take a look at the elements of a chi-square test. So again, dividing this in two types, the test of independence and the goodness of fit, I have these fictitious examples. So if we look at the test of independence, we need two independent variables. And for a chi-square, these independent variables would be either nominal or ordinal. They're measured at the nominal or ordinal level of measurement, and most commonly at the nominal. So an example of the nominal level of measurement can be found here to the right. We have fall, spring, and summer. So consider that you have some sort of specialized counseling training program, and you have different instructors teaching this program, and you have a fall, a spring, and a summer set of instruction. And you look at the nature of how the courses are arranged, you look at the instructors, and you think that there may be a difference in how well students do, even though it's the same instruction, how well the students do by semester. So is there a difference in the number of students that pass the specialized counseling training program versus failing it by semester? Fall, spring, and summer in this example, they are nominal variables. You can't order the 3 semesters. They're nominal, name only. We have the same situation with the other independent variable here, the pass and fail, the outcome variable. Pass and fail are at the nominal level of measurement. You can't put one before the other. The ordinal level of measurement has all the characteristics of the nominal level of measurement, except the observations can be ranked. The distance between the observations, however, still does not have meaning like you would see at the interval or ratio level of measurement, where the distance has meaning. So at the ordinal level, you could consider first, second, and third in a race. You know who finished first and who finished second and who finished third, but you don't know how much distance there was between the first and second place finish and the second and third place finish. So they're ranked, but the distance is not meaningful. With the goodness of fit, you have one independent variable, again at the nominal or ordinal level of measurement, and you compare this independent variable to an expected distribution. We oftentimes see the goodness of fit when we're working with some sort of known probability. So in this example here to the right, I have heads and tails, so this is a coin toss, and you have observations. You had 8 times where you had heads, 12 times where you had tails, and of course the expected distribution would be equal. There's a 50-50 chance for any particular observation. So for both the heads and tails categories, you would expect 10. I have both of these examples in tables, and when you work with chi-square, these are referred to as contingency tables. And the values are placed in cells. So in that top right contingency table with the semesters and the outcome variable, we have 6 cells. In the bottom contingency table, we have 4 cells. The cells contain the actual counts, the frequencies, the number of times that we made a particular observation. So in both of these examples, we're really looking for the same thing. If you consider the fall, spring, and summer example with pass-fail, you're looking at these counts and wondering if there's any real difference between these different semesters, if the students are performing the same or differently by semester. Normally, to determine something like this, we would use a parametric statistic. However, here we only have the frequencies. We have the number of students that passed in the fall, the number that failed in the fall, and the same information for spring and summer. So when working with data that have violated the assumptions of parametric statistics, that might be a time to use chi-square, as I mentioned before, or when you have frequencies or counts. That's also an opportunity to use chi-square. For the goodness of fit, we have an expected distribution that's given to us as part of the design, like in this example with a coin toss. For the test of independence, as a part of that process, the expected values for each cell are calculated, and the actual observations are compared to those expected values. The equation for calculating the expected values is the row total multiplied by the column total divided by the total sample size. So in this example, the row total would be 40 plus 26. The column total would be 40 plus 45 plus 37. Those two totals would be multiplied together, and that would be divided by the sum of all of the values from all 6 cells that we have here. So we're comparing actual values to expected values. Now let's take a look at the assumptions for a chi-square test. So just like parametric statistics, non-parametric statistics have assumptions. Our data need to meet certain assumptions so that we can have some confidence in the result. The first assumption for chi-square is the assumption of independence of observations. So all the observations for a chi-square must be independent. Therefore, the chi-square test is not ideal for a pre-test, post-test design. By nature, the post-test will be dependent on the pre-test, the post-test value dependent on the pre-test value, and that would not be consistent with independent observations. The next assumption deals with the sample size, and there are a few rules here. We referred in the last slide to the idea of contingency tables, and we have a certain number of cells. In the test of independence, it was a 3 by 2. It was fall, spring, and summer by pass and fail. In the goodness of fit example, it was 2 by 2. Heads and tails, and observed and expected. Each one of those counts is in a cell. So the sample size for a chi-square is governed by a few rules. At least 80% of the contingency cells must have an expected value greater than 5. And again, that expected value is calculated by taking the row total for any particular cell, the column total for that same cell, multiplying those two values and dividing by the sample size. And that's the total sample size. That's all the counts from every cell added together. In addition to that rule, no cell can have an expected value less than 3. When working with chi-square, it's ideal if we can get a sample size that is greater than the total number of cells multiplied by 5. So in that first example with that 3 by 2 contingency table, that's 6 cells multiplied by 5. We'd want a sample size greater than 30. And the last assumption for chi-square is that the data must be expressed in frequencies or counts. So in the example with the semesters and the pass-fail, each of those values in each of those cells is a count. It's the number of students for that semester that passed or the number of students that failed. Those are correctly expressed as a count, a frequency, the number of times something occurred. A cell cannot be populated with a percentage or some other transformation of the data. Chi-square statistic only works with frequencies. I hope you found this introduction to chi-square to be helpful. Thanks for watching.